In a piecewise function, we have different rules for different parts of the domain. So if we look at the first function, number 1, g of x equals x plus 2 if x is greater than or equal to 3. Otherwise, it's going to equal negative x plus 2. So when we evaluate a piecewise function, we first have to decide which function rule applies to that particular x value. So when we look at g equals 0, we see that is where x is less than 3 here. So we're looking at the second part of the rule. So g equals 0 is negative 0 plus 2, which is 2. Now when g equals 3, we're looking at the top rule because this is where x is greater than or equal to 3. This is where x is less than 3 but not equal to 3. So for number 3, we're saying we're applying this particular rule. So we say g of 3 is 3 plus 2, or 5. And g of 6 also applies to the top rule. G of 6 is 6 plus 2, which is 8. Now, what I suggest you do, I don't think that's terribly difficult. Why don't you take a look at number 2 and turn off the video and see if you can do it, and then I'll talk through the answers and you can check and see if your answers are right. Okay, for the first one, when h is negative 1, we're in this part of the domain. So the absolute value of negative 1 is 1. When h is equal to 4, we're in this very limited part of the domain. This rule only applies when x equals 4. We have 4 minus 1 is 3. Then when h is 7, fooled you, it doesn't actually exist because this third rule only applies when x is between 4 and 6. 7 is not included in the domain at all. So there is no y value when x equals 7. Now let's look about how do we graph a piecewise function. The first two are partially done for you, and we're just going to complete them, and the third one we'll do completely ourselves. So first of all, you notice that we have the graph of x squared in this gray part right here, and the other graph is the graph of the function 2x minus 4. And just to remind you, when you see a linear function, if you can, the easiest way to do this is to graph the y-intercept, which is negative 4, and then count over 1 and up 2 and graph another point for the slope. And so you can quickly graph it just using the y-intercept and counting over and up to graph other points. You can also make a t-chart and graph it if you want to. But what I usually do, what I suggest you do, is you take the different individual functions and you just graph them very lightly with dotted lines. And then go back and we're going to darken the portions that actually are part of the function. So we're going to look at our first domain section when x is 0 to 2. So we're going to be on the graph x squared. So when x is 0, here's the point on x squared. Notice that is equal to 0, so I use a closed circle here. When x is less than 2, since it's less than but not equal to, I'm going to use an open circle for 2. When I go over to 2 on the x-axis and go up to my x squared function, there is the value on the graph of x squared when x is 2. And then I'm going to fill in everything in between. So that section of the graph is part of my piecewise function. Then the line is the rule when x is greater than 2. So I'm going to go over on the x-axis where x is 2. That's where I start, and that's an open circle because that is not included. It's just greater than 2. And then anything where x is greater than 2, I will be on this line. So that's the entire graph. The rest of the grayed out part is not included. So when we look at the domain of this function, we're looking at all the possible x values. And really that's not too hard because you can combine together what's in here. Okay? So we have in our domain, x is an element of 0, 2, open endpoint. Now notice 2 is not included in either of these sections, so I can't just go from 0 to infinity. I have to say 0 to 2 and then put this union sign saying or 2 to infinity but there's actually a gap in the graph. If I look at the value x equals 2, there is no y value when x is 2 defined in this function. Now range, I'm looking on the graph. I see values from 0 to 4 here, and from almost 0, close to 0, up to infinity here. So basically anything from 0 to infinity on the y-axis will contain will correspond to the point on the graph. So y is an element of 0 to infinity. Now here we have three different graphs. Negative x squared plus 6, which is this upside down parabola here. We have the absolute value of x, this v-shaped graph, and we have 2x minus 5, which is this line. A portion of each of these graphs is used depending on these different domains. So if you want to, pause the video and see if you can do it, and then I will go ahead, and if you want to follow along, I'll just talk it through. Okay, the domain here, x is less than negative 2, not including negative 2, so there's going to be an open circle involved here. So I'm going to find negative 2. I'm going to go over to the graph of the parabola and find my first point, which is on the parabola, and then anything less than negative 2 is going to be a point on the parabola. So that's going to be all of these values here. I actually want to do that in red because I think it shows up a little better. Okay, so there is all of those values. Now for the absolute value graph, I'm going to be starting where x is equal to negative 2. So I actually fill in the circle here because that point is where they overlap, and I'm going to where x is less than 3. So I'm going to find 3 on the x-axis, go up to the absolute value graph, and draw an open circle here. So this is an open circle, closed circle. Everything in between those two numbers is a point on the graph of the absolute value graph. Then where x is greater than or equal to 3, so once again where x is 3, now I'm going to find the point on the line 2x minus 5. That's a closed circle because it's greater than or equal to, and everything greater than 3 then is a point on this line, so this section of the graph. Now when we look at domain and range, look at your x values. It goes from x is less than negative 2, so from negative infinity to x is greater than 3. And do I have any gaps in between? No, we do not, because where x is 3, it's an open circle here but a closed circle here, so there is a y value for x equals 3. It's right here. There is a y value for every x value, because this continues to go out as an up and this continues to go out and down. So all x values are included in this domain. So x is an element of negative infinity to infinity. Now you don't absolutely have to write the x as an element, but I'm just trying to reinforce that domain is x and range is y. So if you don't include that in, that's not wrong. Now range. So starting out, if you look at the y-axis, for every y value, is there a point on the graph? Sure looks like it, because it goes up and down to infinity, and every place I look, there is no gaps. Because notice right here, there's a hole here, but there's an x value or a y value over here, an x value over here that goes with that y value. So every point has every y value has a corresponding point on the graph, so that's negative infinity to infinity as well. Now what happens when you have to start totally from scratch? Well, you actually have to sketch these graphs. So let's start with x plus 3. X plus 3 is a slope of 1 and a y-intercept of 3. So I'm going to go over and find my y-intercept of 3, and I'm going to go over 1, up 1, over 1, up 1, over 1, up 1. So all of these points are points on the graph. And remember, I don't want to draw a solid line, just kind of a light dotted line right now to show these are my points. It's a little easier to draw a light dotted line with a pencil. Okay, then my second graph is the graph y equals 1. Well, that just means a horizontal line at 1. So that's my graph, that's number 2. That's my second graph. So number 1 is here, this one's number 2. My third one is negative 2x plus 6. The y-intercept is 6, so if I count up the y-axis till I get to 6, then the slope is -2, which means I'm going to go over 1 and down 2. So I'm doing this, over 1, down 2, over 1, down 2, over 1, down 2. So as I do this, I'll get these points right here. And I'm going to try to draw a little dotted line. Okay, down like that. Okay, now I'm going to go through and put in my domain restrictions. So for the this is number 3 here. So for the first graph, number 2, I only want the section where x is -3 or -1, or what's in between those. So starting with x is -3, I go to my line number 1, and this is equal to, so this would be a closed circle. 1, 2, 3. So right here, where it crosses the x-axis is where I'm looking. Then it's less than -1, so I'm going to have an open circle here and then everything in between. So at -1, I go up to that line, put an open circle, and this is the section of the graph I'm using that's in my function. From -1, closed circle, to 2, open circle, I'm going to be on the line y equals 1. So from here to +2 to here, I'm on the line y equals 1. Now the last one, the last graph, is going to be when x is 2 to when it's 3, I'm going to be on the line -2x plus 6. So that's from here to here. Now it looks kind of like they cross over. They don't actually cross over. They're very close together, but that little section here. So notice for this x value -1 and for this x value 2, there is a corresponding y value. You notice that if I drew a vertical line through here, it would cross through a hole here and then through a point, a hole and a point. So this is still a function, and every x value in between these 2 points has a y value. So my domain is going to be from -3 to +3. With closed brackets because both endpoints are included. My range goes from 0 to 2, and so there's no gaps in between. There are y values everywhere from 0 to 2. Alright, the next step now is, can we go the other direction? Can we write a piecewise function that models the graph? So I have 3 sections to my graph here. Section number 1 is this line here. Section number 2 is the line segment going downward, and section number 3 is the line segment going upwards. Now I want you to notice that these are not quite the same slope. If they were the same slope on both sides, only opposite, like this was a -2 and a +2 slope, I could write this as an absolute value graph. But this one has a slope of over 1 down 2. So this one has a slope of -2. This one has a slope of, this looks like over 1 up 2, but if you go over here, it's not the same here. See, it's different. So I think what I'm going to have to do on this third one, I'm going to move number 3 out of the way here, is I'm going to actually have to count over 3 and up 4. This is 3 and this is 4. So this has a slope of 4/3. Wait, 1, 2, 3, 4, 5. That's 5, not 4. Over 3 and up 5. So this has a slope of 5/3. This has a slope of -2. What does this have a slope of? If I go over 2 and up 1, this has a slope of 1/2. Okay, so this has a slope of 1, and then this would be -2 as we move from left to right. This has a slope of 1/2. This has a slope of 5/3. I'm going to show you a couple ways to find the equations of these lines, and then you can decide kind of how you would like to do this. Number 1, I can pick a point on the line, which is -1, 1, 2, 3, 4, 5, -1, 5, and I know the slope is 1/2, and I can use y equals mx plus b. So I can say 5 is equal to negative 1 times 1/2 plus b. So 5 is equal to negative 1/2 plus b. If I add 1/2 to each side, then I get 5.5, or 5.5 equals b. So I can say y equals 1/2 or 0.5x plus 5.5. That would be my equation. But let me show you a nifty trick. That one's not too bad, but it gets kind of nasty doing that method with some of the others. I'm going to show you something really quickly. Let's say that I had a graph. So I'm going to draw a little, just sketch a little graph here. And I have a line that goes through here, and it has a point at 0, 0. Okay, and I'm going to do something. I'm going to group these together so they'll move together. Okay, and let's say that this line has a slope of 2. We'll just say slope equals 2. And let's say that I shifted that line over 1 in the left, or to the left 1, and up 5. So now it's up here. So now, and that doesn't really look like it has a slope of 2, does it? But let's just use our imagination. Okay, so now that point that I'm talking about, that blue point, is this point here. Now we learned when we did transformations of sinusoidal functions that shifting to the left was the same as subtracting or adding 1 inside the function, shifted the graph to the left 1, and then adding 5 outside the function shifted it up. So if my original function down here is y equals 1/2 x, and then I shift it left 1 and up 5, that would be the same as saying y is equal to, let me move that just a little bit. Sorry, I don't have enough room. That would be the same as saying y is equal to 1/2 times x plus 1 plus 5. I've shifted it to the left 1, that's what this part does, and then up 5. So I can say y is equal to 1/2 x plus 1/2 plus 5. So y is equal to 1/2 x plus 5.5, or 5.5. 0.5x plus 5.5, exactly what I just got. Okay. Now you might think that took just as many steps as this did, and you're right, it did. But sometimes it's a lot easier, just depending on what you're doing. So I'm going to do the second one. The second one, we start out with number 2, y is equal to negative 1/2 x. Okay, but it's been shifted to the left 1. So basically you can pick any point on the graph to be your shifting point. So if I look at this point right here, this end point, that's at negative 1, 0, I can just say, hey, this is the graph of y equals negative 2x, but it's been shifted to the left 1. So I can just say negative 1/2 times x plus 1, which is y equals negative 1/2 x minus 1/2. That's pretty easy to do. That is a simpler way to do it, except I just did something wrong. That doesn't have a slope of negative 1/2. That has a slope of negative 2. Back up, try this again. Y is equal to negative 2x, negative 2x plus 1. So y is equal to negative 2x minus 2. Now I could have also looked at the fact that it goes through negative 2 on the y-axis and said, oh, that's my y-intercept there. Same thing, negative 2x minus 2. So there's another way of looking at it. You could also go through the whole find y, put a point in, do y equals mx plus b. That will work as well. So here's my equation of my first section of the graph. Here's my equation of the second section of the graph. When I get to the third section, this little method of shifting is really going to come in handy. So I have this point right here. This is the point 2, negative 6, if you count the little boxes. So basically I could think of this is a graph with a slope of 5/3. Imagine that this point originally was at the origin and then I shifted it right 2 and down 6. So the whole graph has been shifted right 2 and down 6. I want to stress that this works for any point on the graph. I could use any point and get the same equation by doing this shifting and translating method. So I'm going to say y is equal to 5/3 times the quantity x minus 2 minus 6. So I've shifted to the right 2 and down 6 from my original graph of 5/3 x. So y is equal to 5/3 x minus 10/3, and then so that I can add these two together, I'm going to make this minus 18/3. So y is equal to 5/3 x minus 28/3. Believe me, if you did that the method y equals mx plus b method, it would take a lot longer. Now, just to show you that it doesn't matter what point I pick, what if I pick this point here? This is the point 1, 2, 3, 4, 5, negative 1. If I apply that same method to this point and say, my original graph, when it goes through the origin, would be y equals 5/3 x. Now it's shifted to the right 5 and down 1. This would be 5/3 x minus 25/3 minus 1, which is 3/3. That's still 5/3 x minus 28/3. Okay, so this is a really cool way to write the equation of a line using translations instead of y equals mx plus b. All right. Now I still need to write the actual piecewise function. I have my three equations now, 1, 2, and 3. I've got them where I can see them. So now I have to look at my graph. Notice that this section, look at the domain for section 1. The domain continues going, so we're going from, this will go all the way to negative infinity in the x direction, but it stops at x equals negative 1. So I'm going to say that the first equation applies, f of x is equal to 0.5x plus 5.5 for x less than or equal to negative 1. Notice it has a closed circle here, so I can say less than or equal to. The middle section of the graph goes from x equals negative 1 with an open circle to x equals 2 with a closed circle. So I'm going to say negative 2x minus 2, that graph applies when negative 1 is less than x is less than or equal to 2. So when x is in between negative 1 and 2, not equal to negative 1 but equal to 2, this function is the rule. The third function, 5/3 x minus 28/3, and I apologize for the nasty numbers, didn't realize how bad it was when I did this graph. 5/3 x minus 28/3, that section, that rule applies when x is greater than 2. I can't say greater than or equal to 2 because I've already used the 2 in this part of the domain. So basically what you have is an open circle overlapping a closed circle right here. And so we say x is greater than negative 2. So that section of the graph is applied for x is greater than. Now if I had used just greater than here, or just a less than sign here, I could have used an equal sign here. It doesn't really matter because since they overlap. Okay, that is the end of the piecewise function section. Actually, I lied. I wanted to tell you that there is another video that gives instructions for doing these kinds of functions on your calculator, so and on Desmos. So I wanted you to take a look at that as well.